All right, strap in, everyone. Today, we're diving deep, deep into the world of black holes. And I gotta say, this is not the stuff they taught us back in school.
Yeah, it's definitely not your high school physics class.
We're talking some seriously mind-bending physics here, folks. All based on, well, this paper. It's called Spacetime Branching in Spherically and Axially Symmetric Gravitational Collapse.
Catchy, right?
The author is Sabir A. Rahman. And trust me, this deep dive is going to challenge, like, everything you think you know about black holes.
Yeah, it's a pretty big departure from the traditional view, that's for sure.
What if, instead of being destroyed, matter falling into a black hole is actually shunted off into, like, a hidden parallel region of space-time?
It is pretty radical, but what I find so interesting about Rahman's work is he's not using any exotic new physics. He's using the established principles of Newtonian gravity and general relativity. But he uses them to point out some inconsistencies in our current understanding of black hole formation.
Okay, so let's start with the basics, I guess. The usual picture of a black hole. A region of space-time where gravity is so strong, nothing, not even light, can escape.
The traditional picture is, pretty straightforward. A star collapses under its own gravity, gets so dense that not even light can escape.
Yeah, the classic, like, cosmic vacuum cleaner just sucking up everything.
Right, exactly.
That point of no return, that's the event horizon. But here's where things get interesting. Rahman argues there's a logical problem with what happens inside the event horizon.
Right.
So explain that.
So the traditional view is that anything that crosses the event horizon inevitably gets crushed into the singularity at the center of the black hole, right?
Right.
But Rahman points out this doesn't quite add up.
Well, Rahman, he starts by pointing out a paradox with this classic picture. It has to do with the matter inside the black hole and how it's affected by gravity.
Okay.
See, according to both Newton's laws of gravity and Einstein's theory of general relativity, matter at a certain distance from the center of a collapsing star should only feel the pull of gravity from the matter within that distance.
Okay.
Not from anything further out.
So like if you were to draw a circle around part of the star, the stuff inside the circle is only affected by the gravity inside the circle, not by the stuff outside the circle.
That's exactly right.
Even though it's all collapsing together.
Exactly. Think of it like nesting dolls.
Okay.
Each layer is only influenced by the layers within it, not the ones outside it.
Okay.
So how can all the matter inside a black hole be constantly pulled toward the singularity if it's not being influenced by the stuff further out? That's the paradox.
Yeah, that does seem like a disconnect. If the gravity of the outermost layers of a collapsing star isn't affecting the stuff closer to the center, what's driving that continuous collapse into the singularity?
That is the million-dollar question. So how does Rahman resolve this?
Well, his proposal is that space-time itself must branch at the event horizon.
Right.
The idea is when a black hole forms, space-time itself, like, splits into two separate branches. It's like a fork in the road.
So there's like two separate realities almost.
Each branch has its own set of rules, its own kind of reality, yeah.
Okay, I'm definitely intrigued, but like that sounds, I don't know, pretty out there. Okay, I'm going to need some help visualizing this branching process.
All right, so picture this. Take a look at figure 1 from the paper. Imagine two spherical shells of matter. One just outside the forming black hole, and one just inside. At the moment of formation, they're both at the event horizon. But they're subject to different rules. The outer shell must continue to fall inwards, while the inner shell is actually free to move outwards.
But that creates a paradox, right? Because they're at the same point in space.
Yeah. And that's the crux of Rahman's argument.
Okay.
The only way to reconcile this contradiction is to say that these two shells are no longer part of the same space-time.
They've branched off.
They've branched off, into separate regions, each with its own metric.
Now, I'm guessing not everyone is familiar with the term metric.
Right.
Can you give us a quick, explanation?
Yeah. A metric is essentially a mathematical structure. Defines how distances and time are measured in a given region of space-time. It's like the set of rules that govern the geometry of that region. So in Rahman's model, the branch containing the singularity would have the usual Schwarzschild metric, but the matter branch would have a different metric altogether.
So instead of being crushed into oblivion, the matter that was collapsing to form the black hole ends up in this separate matter branch with its own unique set of rules. And what's even more interesting is that this paper argues that the matter in this branch isn't just frozen in time.
Really?
It can continue to evolve, interact, and even form more black holes.
Wait, are you telling me there could be black holes inside other black holes?
That's what the research suggests.
Like a whole chain of them, each with its own little universe inside. That's insane.
It leads to the idea of a hierarchy of black holes, each with its own separate spacetime branch.
Raman argues that this matter branch must also have an exterior region, and he even derives a possible metric for it. His findings suggest that this exterior region acts like an inverted black hole.
An inverted black hole.
Yeah.
Okay, hold on. I thought that the whole definition of a black hole was that nothing, not even light, could escape. How can a black hole be inverted?
Right. It's a pretty wild concept. Basically, imagine a black hole in reverse.
Okay, in reverse. So instead of pulling things in,
It pushes things away.
it's like a black hole that's exploding outward.
You could think of it that way, yeah. It's a region of spacetime where the direction of gravity is flipped.
So once you cross the event horizon, you're constantly being pushed further away.
Exactly. There's no going back.
Okay. I'm trying to wrap my head around this, but is this just like a theoretical idea, or is there some actual math behind it?
Oh, there's a math. The paper, it actually uses Einstein's theory of general relativity to model this branched space-time.
Okay, so it's not just like a thought experiment.
No. And what they found is that the math, it actually predicts these inverted black holes. It's like they stumbled upon a bizarre mirror image of a regular black hole, just hidden in the equation.
So if we could somehow travel to the matter branch of a black hole, we'd encounter this inverted black hole pushing us away.
Theoretically.
Instead of being, crushed into oblivion by a singularity, we'd be like flung outwards into, I don't even know.
Who knows where?
That's crazy. Okay, but so far we've been talking about like non-rotating black holes, right? What about the black holes that spin? Those Kerr black holes, aren't those way more common in the universe?
Yeah, you're right. Most black holes are spinning. And this paper, it suggests that this whole space-time branching thing, it applies to them too. So even a spinning black hole would have those separate realities.
Precisely.
Okay, that makes me feel a little better. But what about that inverted black hole? The one that pushes things away instead of pulling them in?
Yeah, the inverted black hole still forms in the rotating case.
Really?
But it's even more fascinating.
How so?
Well, Raman actually came up with a possible mathematical description for it.
A mathematical description?
Yeah, something called a metric.
Remind me what a metric is again.
It's basically a set of equations. That tells you how space-time is curved in a particular region.
Okay, so it's like a blueprint for gravity?
Exactly.
Yeah.
And Raman figured out the blueprint for gravity around this inverted, rotating black hole.
Wow. That's some serious math.
It is, but it tells us some incredible things about these inverted black holes.
Like what?
Well, for one thing, the location and nature of their event horizons, those boundaries where nothing can escape, they depend not only on how fast the black hole is spinning,
but on something else too.
Yeah, they also depend on how the matter is distributed inside the matter branch.
Oh, wow. So depending on what's happening inside that pocket universe, the inverted black hole could behave very differently.
Absolutely.
This is mind-blowing.
There are even some scenarios where a second horizon could form.
A second horizon?
Yeah, imagine this. A particle escapes from the matter branch.
Okay.
It passes through the inverted black hole's event horizon.
It's free.
But then, it encounters another horizon.
It's like escaping from one prison just to end up in another.
Exactly.
This is giving me a serious existential crisis.
And this brings us to one of the most mind-boggling implications of Raman's work, the possibility that our own universe might actually be the interior of a supermassive rotating black hole in some larger superuniverse.
Right. It's a bold claim, but it's a logical consequence of his model. If space-time branches at the event horizon of every black hole, and if our universe was born from the collapse of matter inside a black hole in some larger parent universe, then we could be living inside that very branch.
It's a fascinating possibility, and it's not even a new idea.
Oh, really?
Physicists have been playing with this concept for decades, going all the way back to Eddington in the 1930s. I'm trying to picture this. If we're inside a black hole, wouldn't we be able to see the event horizon, like the boundary of this other universe?
Well, that's where the inverted black hole comes in. Remember, it pushes everything outwards.
Right.
So what we perceive as the blackness of space, the seemingly empty regions between galaxies, that could actually be the event horizon of the inverted black hole that surrounds our universe.
It's like a cosmic wall.
Yeah, like a wall preventing us from seeing what lies beyond.
So this This could explain why the night sky is dark.
Exactly.
Because if the universe is infinite and it's full of stars, shouldn't every point in the sky be, like, blazing with light?
That's Olber's paradox.
Right, Olber's paradox. So this inverted black hole thing, it solves that.
It's a possible solution, yeah. If we're inside a black hole's matter branch, the inverted event horizon would block any light coming from, outside our universe.
Okay, my head is spinning. So to recap, our universe is inside a black hole. That black hole could be inside another universe, which could be inside another black hole, and so on. This is a lot to absorb. We've gone from the basics of black holes to the idea of branching spacetimes and inverted black holes, and now we're contemplating the possibility that our entire universe is tucked away inside a black hole in some larger super-universe. What are the implications of this radical shift in perspective? Where does it lead us?
That's precisely what we'll explore in the next part of our deep dive. We'll delve into the potential ramifications of Raman's findings for our understanding of the universe, from the information paradox to the nature of reality itself.
I, for one, can't wait to hear more. Stick around, listeners, because this deep dive into the heart of black holes is far from over.
Welcome back. So let's unpack some of these profound implications of Raman's model. Let's start with a concept that's been a real head-scratcher for physicists, the black hole information paradox.
Yeah, I remember hearing about this paradox, but I'll be honest, it always seemed a bit abstract.
Yeah.
Can you, remind us what the issue is?
Sure. So at its core, the information paradox is this conflict between two of our most fundamental theories of physics.
Mm-hmm.
You got general relativity and quantum mechanics.
Right.
General relativity suggests that anything that falls into a black hole, it's lost forever, swallowed up by the singularity.
Right.
But quantum mechanics has this strict rule. Information cannot be destroyed.
So if black holes are truly these cosmic vacuum cleaners that gobble up everything, wouldn't that violate the laws of quantum mechanics?
Exactly. And this has been a major source of debate for decades now. Physicists have been grappling with, how do you reconcile the seemingly information-destroying nature of black holes with this fundamental principle of information conservation?
So how does Raman's model, this branching spacetimes, offer a solution to this paradox?
Well, remember, in Raman's model, matter falling into a black hole, it doesn't get destroyed at the singularity. Instead, it's shunted off right into the separate branch of spacetime, this matter branch. So the information contained in that matter, it isn't truly lost. It's just hidden away in a region of spacetime that we can't access from our own branch.
Okay, so it's like the information goes into a cosmic vault, inaccessible to us, but still preserved.
Yeah, you could think about it like that.
I'm starting to see how this could be a game changer for our understanding of black holes.
And this, it ties into another fascinating aspect of Raman's work, his suggestion that there could be this whole hierarchy of universes nested within each other.
This idea of a hierarchy of universes. This sounds like something straight out of science fiction.
Right.
Walk us through how that concept arises from his model.
So imagine if every black hole creates a new baby universe through this space-time branching process, and those universes contain their own black holes,
right,
which in turn create more universes, and so on.
Yeah.
You end up with an infinite chain of nested universes,
Whoa.
each with its own unique set of physical laws and properties.
So our universe could be just one tiny bubble in this vast cosmic foam of interconnected universes.
That's one way to visualize it, yeah. And it raises some pretty profound questions about the nature of reality itself. If our universe is just one branch on this massive cosmic tree, does that change how we view our place in the grand scheme of things?
It definitely challenges our sense of uniqueness, that's for sure. Instead of being the center of everything, our universe becomes just one of countless possibilities.
Right.
Each with its own unique history, its own laws of physics, maybe even its own forms of life.
So we're not as special as we thought we were.
It's a humbling thought, isn't it?
What about life in those other universes? I mean, if there are countless worlds out there, each with its own unique set of conditions, the chances of life arising somewhere else, they got to be pretty high, right?
It's definitely a possibility. But, okay, this whole concept of space-time branching, it has some pretty big implications, right? I mean, how does it change the way we think about, black holes themselves?
Well, one major thing is that it suggests that black holes don't actually grow in mass after they form.
They don't grow.
All the matter that falls into a black hole, after its creation, it ends up on the Schwarzschild branch, not the matter branch.
So the matter that originally collapsed to form the black hole, that initial seed. That's it.
That basically determines its properties forever. Yeah, it never gets any bigger.
So no more cosmic vacuum cleaner.
Not in this model, no. It challenges that classic image of black holes as constantly, growing and gobbling up everything around them.
That's a pretty big change. But wouldn't that contradict what we know about, like, Hawking radiation? Don't black holes slowly evaporate over time, losing mass?
That's a good point. If black holes truly have a static mass, it definitely raises some questions about how Hawking radiation works, and it makes us rethink, you know, what happens when two black holes collide? If they don't actually grow in mass, what happens? Do they create yet another branched reality when they merge?
These are some pretty big questions. But before we get too lost in the multiverse, I want to circle back to something we touched on earlier. Raman's suggestion that black holes might actually be the fundamental building blocks of matter.
Right.
This is the concept that really captured my imagination.
It's definitely one of the most intriguing aspects of his work. It's a bold claim, but, he makes a compelling argument based on the unique properties of black holes.
So what are some of those properties that make black holes potential candidates for being, like, the fundamental particles of matter?
It seems wild, but there's something kind of neat about it. Black holes, they have mass, they spin, just like those particles. And Raman says charge, another fundamental property, it might come from how these tiny black holes behave.
So instead of charge being something a particle just has, it's more like something it does.
Exactly. It could be how these mini black holes, how they interact with space-time, their spin, maybe even connections to other branches. That creates what we see as electric charge.
So like electromagnetism, all those forces, light, electricity, they're just mini black holes doing their thing.
And perhaps most importantly, they're incredibly stable.
So are you suggesting that, like, the familiar particles we know and love electrons, protons, might actually be tiny spinning black holes? It sounds almost too strange to be true.
It's definitely a radical departure from the standard model of particle physics. But if you think about it, the idea has a certain elegance to it. Instead of having this whole zoo of different fundamental particles, we might have just one, the black hole.
It would certainly simplify things.
Right.
But I imagine there are some pretty big hurdles to overcome before we can definitively say that electrons are actually tiny black holes whizzing around atoms.
But hold on, if electrons are like tiny black holes, wouldn't they have their own matter branches and inverted horizons too?
Theoretically, yeah. We are talking about black holes on a scale way smaller than we can even observe right now. The implications of that are huge. It would change everything about how we understand particle physics.
Absolutely. For one thing, we'd need a way to reconcile the immense density of black holes with the relatively diffuse nature of atoms. And we'd have to explain how these black hole particles interact with each other to produce the forces and fields we observe in the universe.
So while the idea is fascinating, it's still very much in the realm of speculation at this point.
Right.
But even if it turns out not to be true, it's a testament to the power of Raman's work that it can lead us to consider such radical possibilities.
I agree. Raman's paper has really opened up this Pandora's box of mind-bending ideas, forcing us to confront, some of the most fundamental questions about the universe and our place within it. It's a reminder that even in a field as advanced as physics, there's still so much we don't know.
And perhaps the most profound discoveries are yet to come. But before we venture further into the unknown, I think we need to take a step back.
Yeah.
And let these ideas sink in. We've covered a lot of ground in this part, from the information paradox and the hierarchy of universes to the mind-boggling concept of black holes as fundamental particles.
Yeah, let's take a moment to process all of this before we delve into the final chapter of our deep dive.
We'll be back soon, listeners, to explore the philosophical implications of Raman's work and what it all means for our understanding of reality itself. Stay tuned. Welcome back to the deep dive. After that last discussion about universes inside black holes and the possibility of black holes being the building blocks of everything, I found myself just staring up at the night sky like, am I looking at reality? Or just a tiny piece of something much, much larger?
It's definitely awe-inspiring to contemplate the sheer scale and complexity that Raman's ideas hint at. It really makes you realize how much is still out there to discover and how much our understanding of the universe could change in the coming years.
We've explored some mind-boggling concepts in this deep dive, but I think it's time to grapple with the ultimate question. What does Raman's work tell us about the nature of reality itself?
That's a profound question, and honestly, I don't think there's a simple answer. But I think one of the key takeaways is that reality might be far more intricate. and interconnected than we ever imagined.
One of the ideas that keeps coming back to me is this concept that our universe might be the interior of a black hole. If that's true, it really flips our perspective on what we consider the beginning and end of things.
It does, doesn't it?
Yeah.
What we traditionally think of as the end, the singularity at the center of a black hole, could actually be a transition point, a gateway to another region of space-time. And the Big Bang, the event we consider the beginning of our universe, might have been the result of a collapse in some prior parent universe.
So instead of a linear progression from beginning to end, we might be part of like a cyclical process of expansion and collapse, birth and rebirth, playing out across, a vast cosmic landscape of interconnected universes.
It's certainly one interpretation, and it's definitely a captivating one. But even if we set aside this idea of a cyclical universe, the concept of branching space-time's challenges, like our fundamental assumptions about time and space. If reality is constantly branching, creating new universes with each black hole that forms, then the traditional notion of a singular unified timeline, it starts to break down.
Makes you wonder if those branches ever, reconnect or interact in any way. Are there other versions of ourselves out there living in those parallel branches? I mean, it's enough to send your head spinning.
It's a tempting thought experiment, and one that, science fiction writers have explored for decades.
So where do we even go from here? How do we figure out if any of this is true?
That's the challenge, and the cool part about this kind of theoretical physics. We might not be able to see these things directly, but there are still ways to test the ideas.
And one promising path is through studying gravitational waves.
Right, those ripples in space-time. We've been able to measure them here, haven't we? And Raman thinks those space-time branches might leave a unique fingerprint on those waves, especially when black holes collide, like echoes or distortions that wouldn't be there otherwise.
So if we can study those waves closely enough, we might find evidence for those hidden branches. It's like using the entire universe as our lab.
But hey, remember that crazy idea of our whole universe being inside a black hole? You mentioned it might be testable. How could we ever know if that's true?
Yeah, that one's been bugging me. It's such a huge concept, hard to even wrap my head around, let alone test it. But you said there might be some clues.
Maybe. Remember Olber's paradox, how a giant inverted black hole around us could explain why it's dark at night?
Right, because light from outside our universe would be stuck behind that horizon, like a cosmic curtain.
Exactly. We can't see that super universe directly, but maybe there are tiny clues in the cosmic microwave background radiation.
The Big Bang afterglow, what kind of clues?
Well, if we're really inside a bigger structure, there might be weird patterns in that radiation, things you wouldn't see in a regular universe. Little fingerprints from the super universe.
So we got to study this ancient radiation super carefully, and maybe we'll find hints of something bigger out there. It's like space archaeology.
Kinda. It'd take really precise measurements and fancy math, but it's one way to test this mind-blowing idea.
It's unbelievable. We started by wondering what happens inside black holes, and now we might rewrite physics. It's kind of overwhelming.
It is amazing, isn't it? This whole thing started with a simple question, and it's led to a whole new understanding of the universe.
Well, on that note, I think it's time to shift gears a bit. Remember how you mentioned that Raman built on some earlier work? I'm curious to hear more about the history of these ideas. Were there any hints that something like this might be true before Raman came along?
That's a great question. Raman's work definitely didn't come out of nowhere. He's building on decades of research, and there were definitely some hints along the way. He even cites a paper from way back in 1958 by David Finkelstein that suggested there might be something strange happening at the event horizon.
Finkelstein back in the 50s. Wow. So what was he onto? What kind of strange stuff at the event horizon?
Well, he, along with some other physicists like Brillouin and Bonner, they were looking at the geometry of space-time when stuff collapses. They were puzzled, like how can the matter keep its shape while falling into the Schwarzschild interior, which has a totally different shape.
Sounds like trying to fit a square peg in a round hole, but with cosmic geometry.
Exactly. They basically pointed out these inconsistencies, that we need a better picture of what happens at the event horizon. And that's where Raman's model comes in. It solves these issues with this branching space-time idea.
So he took these old puzzles and made them fit, huh? Pretty neat.
It is. And not just the geometry stuff. It also supports the idea that a black hole's mass is mostly tied to the event horizon. McRae and Bell, other physicists, they've argued for that too.
So the event horizon isn't just some random boundary. It's super important to the black hole's mass. So much to learn. It's amazing how a simple question about what's inside a black hole leads to all this.
That's the beauty of science, right? Curiosity sparks questions, questions lead to research, and sometimes that research changes how we see the universe.
It's mind-blowing. Ramon's paper has given us a lot to think about. Branching space-time, inverted black holes, nested universes,
Yeah.
even the link to particle physics.
It's a lot to digest, but I think the biggest lesson is to stay open-minded. The universe is full of mysteries, we're just scratching the surface.
And if Ramon's right, those mysteries might be weirder and more awesome than we ever thought. It pushes us to the very edge of what we know, forcing us to question our assumptions and to imagine possibilities that we never even considered before.
Absolutely. It's a reminder that science isn't, a static set of facts, but an ongoing process of discovery and exploration. And who knows what mind-blowing revelations await us as we continue to probe the deepest mysteries of the cosmos.
Well, I think it's safe to say that this deep dive has left us with more questions than answers. But it's also ignited a sense of wonder and curiosity about the universe and our place within it. I'm eager to see how Ramon's work will influence future research and how it'll shape our understanding of the cosmos in the years to come.
I share your enthusiasm. It's an exciting time to be following the frontiers of physics, and it's a privilege to share this journey of discovery with you and our listeners.
Thanks for joining us on this deep dive. We hope it's inspired you to look up at the night sky with a renewed sense of awe and to contemplate the profound mysteries that lie hidden within the fabric of reality.